let's talk now about entanglement. So we talk about entanglement when we have two non-interacting particles. You don't need a strong interaction between particles to produce entanglement. The particles can be totally non-interacting. Suppose particle 1 can be in any of these states, U1, U2. Let's assume just U1 and U2. And particle 2 can be in states V1 and V2. And you have these two particles flying around. These are possible states of particle 1 and possible states of particle 2. Now you want to describe the full system, the quantum state of the two particles. States of the two particles. Two particles. Well, it seems reasonable that to describe a state of the two particles, they're not interacting. I should tell you what particle 1 is doing and what particle 2 is doing. Okay, so particle 1 could be doing this, could be U1. And particle 2 could be doing V1. And in a sense, by telling you that, we've said what everything is doing. Particle 1 is doing U1, particle 2 is doing U2. And mathematically, we like to make this look like a state, and we want to write it in a coherent way. And we sort of multiply these two things. But we must say sort of multiply, because a strange multiplication, this, you know, we think of them as vectors or states. So how do you multiply states? So you put something called a tensor product, a little multiplication like this. So you could say, don't worry, it's kind of like a product. And it's the way we do it. We don't move things across. We list the first state here, the second state here, and that's a possible state. Now, I could have a different state, because particle 1, in fact, could be doing something a little different. Could be doing alpha 1 U1 plus alpha 2 U2. And maybe particle 2 is doing beta 1 V1 plus beta 2 V2. And this would be all right. I'm telling you what particle 1 is doing, and I'm telling you what particle 2 is doing. And the rules of tensor multiplication, or this kind of multiplication to combine those states, are just like a product, except that, as I said, you never move the states across. So you just distribute. So you have alpha 1, beta 1, the number goes out, U1, V1, that's the first factor, plus alpha 1, beta 2, U1, V2, plus alpha 2, beta 1, U2, V1, plus alpha 2, beta 2, U2, V2. I think I got it right. Let me know. I just multiplied and got the numbers out. The numbers can be moved out across this product. Okay, so that's a state, and that's a superposition of states. So actually, I could try to write a different state now. You see, we're just experimenting, but here is another state. U1 V1 plus U2 V2. Now, this is a state that actually seems different. Why different? Because I don't seem to be able to say that what particle 1 is doing and what particle 2 is doing separately. You see, I can say when particle 1 is doing U1, particle 2 is doing V1. And when particle 1 is doing U2, this is V2. But can I write this as some state of the first particle times some state of the second particle? Well, let's see. Maybe I can and can write it in this form. This is the most general state that you can say. Particle 1 is doing this, and particle 2 is doing that. So can I do that? Well, I can compare these two terms with those, and I conclude that alpha 1, beta 1 must be 1. Alpha 2, beta 2 must be also 1. But no cross products exist, so alpha 1, beta 2 must be 0, and alpha 2, beta 1 must be 0. And that's a problem because either alpha 1 is 0, which is inconsistent, or beta 2 is 0, which is inconsistent with that. So no, this state is unfactorizable. It's a funny state in which you cannot say that this quantum state can be described by telling what the first particle is doing and what the second particle is doing. What the first particle is doing depends on the second, and what the second is doing depends on the first. This is an entangled state. And then we can build entangled states, and are very strange states. So with two particles with spins, for example, we can build an entangled state of two spin 1/2 particles. And this state could look like this. The first particle is up along Z, and the second particle is down along Z, plus a particle that is down along Z for the first particle, but the second is up along Z. And these are two spin 1/2 particles, and in the usual notation, these experiments in quantum mechanics, in black hole physics, people speak of Alice and Bob. Alice has one particle, Bob has the other particle. Maybe Alice is in the moon and has her electron, and Bob is on Earth and has his electron, and the two electrons, one in the Earth and in the moon, are in this state. So then we say that Alice and Bob share an entangled pair. And all kinds of strange things happen. People can do those things in the lab, not quite one in the Earth and one in the moon, but one photon at one place and another photon entangled with it at 100 kilometers away. That's pretty doable. And they are in this funny state in which their properties are correlated in surprising ways. So what happens here? Suppose Alice goes, or let's say Bob, goes along and measures his spin. And he finds his spin down. So you look here, here is down for Bob. So at this moment, the whole state collapses into this, because up with Bob didn't get realized. So once Bob measures and he finds down, the whole state goes into this. So if Alice on the moon or in another galaxy at that instant looks at her spin, she will find it up before light has had time to get there. Instantaneously, it will go into this state. People were sure somehow this violates special relativity. It doesn't. You somehow, when you think about this carefully, you can't quite send information, but the collapse is instantaneous in quantum mechanics. Somehow Bob and Alice cannot communicate information by sharing this entangled pair. But it's an interesting thing why it cannot happen. Einstein again objected to this. And he said, this is a fake thing. You guys are going to share, and now, of course, they have to share many entangled pairs to do experiments, so maybe 1,000 entangled pairs. And Einstein would say, no, that's not what's happening. What's happening is that some of your entangled pairs are this, that is, Alice, Bob is down, Alice is up, some of them are this. And there's no such thing as this entanglement. And indeed, if you measure and you find down, she will find up. And if you measure and you find up, she will find down. And there's nothing too mysterious here. But then came John Bell in 1964 and discovered these Bell inequalities that demonstrated that if Alice and Bob can measure in 3 different directions, they will find correlations that are impossible to explain with classical physics. It took a lot of originality for Bell to discover this, that you have to measure in 3 directions. And therefore, the kind of correlations that appear in entangled states are very subtle and pretty difficult to disentangle. So that's why entanglement is a very peculiar subject. People think about it a lot because it's very mysterious. It somehow violates classical notions, but in a very subtle way.